Welcome to the webinar Statistics for Non-Statisticians. I'm your presenter, Jim Johnstone. Today I'm going to show you some ways to take the mystery out of statistical analysis and make it easy and intuitive for non-statisticians to understand. ISO 9004 provides guidance to organizations on how to achieve sustained success through a system of quality management. One of the principles of a successful quality management system is to make improvement decisions using data and appropriate and valid analysis methods balanced with experience and intuition. Statistical analysis is a valid method to compare data, but most of the people in the workplace are not statisticians familiar with these methods. So how can we, as quality professionals, use statistical analysis in a way that makes it intuitive and taps into their everyday experience? We need to make statistical analysis easy for non-statisticians to understand, and we can do that by making simple comparisons and keeping things visual. Get rid of the numbers and Greek symbols and replace them with pictures. But first, let's go over some definitions so we can all be on the same page. A population is all items that come from a common source. A sample is a subset of a population. A statistic is a number that describes a sample. The number comes from analysis of data. The data comes from the sample by measuring or counting. Let's talk about data. Statistics require data, and data can be in the form of specific measurements, counts of things, or ratios of one thing to another. Data is the numeric representation of an observable characteristic of a process or a product. A characteristic is something that describes the product or process. This is usually the thing that you're most interested in when you're making your comparisons. Typical characteristics are weight, dimensions, temperature, color, volume, density, or count. An attribute is a characteristic that a product or process has or does not have. For example, maybe you're only looking at products that pass the test, or that failed the test, or that have more than a certain amount of something. A discrete variable is a characteristic the product can only have in whole numbers. For example, the number of children in a family, or a class, or the sum of numbers on a pair of dice. A continuous variable is one that can be any real number, even though it might be bounded. For example, the weight of a loaded truck. Statistics are often used to compare samples from two populations. For example, let's say there are two ways to make a product, method A and method B. We could have two product populations, A and B, that correspond to the two different methods of manufacture. Statistical analysis helps us distinguish between differences in the populations due to significant events caused by something we did, or random events that are caused purely by chance. When comparing populations, you need a minimum amount of data to make the comparison. Why do you think that is? You're right, because with just a small amount of data, you could reach the wrong conclusion. Here's a drawer full of socks. It contains about 60% white socks and 40% socks that are not white. Let's say those socks were made by method A. If you're drawing samples at random from the drawer to learn what percent of the population was white, how many would you want to pull before you would be confident in your answer? All of them, you say? Oh, it costs you some money every time you pull a sock out of the drawer. So you'd want to minimize the number of samples, but you'd want to have enough samples to make sure that you had confidence in your answer. By the way, what if you pulled all of your socks from the right side of the drawer? Would that be a random sample? Let's test our understanding. The color of a car is a characteristic. It can be an attribute, just like socks. It could be white or not white. Or it could be a variable, white, silver, black, and so on. It could also be a variable if we measure the exact amount of each of the three primary colors that make up the car's color. It's important to identify the characteristic of your product or process that you care about when you're using statistics to compare samples. Here's another example. Let's say you're working at a dairy that produces milk in gallon jugs. Each jug must have at least 1 gallon. The jug holds 2 ounces more than a gallon. You suspect that the filling machine is putting more milk into the jug after maintenance. You carefully conduct a test and you compare it to your prior results. Before the filling machine was maintained, it used 100.9 gallons to fill 100 good jugs. After it was maintained, it used 110.7 gallons to fill 100 good jugs. What have you learned? You're comparing two things: milk used per 100 jugs before and after maintenance. What characteristics do you care about? Well, there's two really: the right amount of milk in each jug and the total amount of milk per 100 jugs. Are these attributes or variables? What do you know after the experiment? Do you know anything about the amount of milk in the jugs? Could that much extra milk be in each jug? Where do you think the milk is going? Maybe you have a leak. Maybe you created some partially filled jugs to make those 100 good ones. There can be more than one important characteristic when comparing samples. If I say go north, what pops into your mind? A picture of something like a compass, or the North Star, the North Pole? Or maybe it's a city north of where you are now. Or is it a number like 360 or 0? We think in pictures, and if we want to communicate quickly and clearly with non-statisticians, we need to paint a picture for them. So let's forget about statistical terms and numbers for a minute and think about painting a picture with our statistical analysis. Here are sample dogs from two populations. Which dog is bigger? Is it significantly bigger? When it's easy to see a significant difference, then usually it's not caused by random variation from one sample to another. We should strive to make the differences easy to see visually. Here's unpopped popcorn from two popcorn brand samples. Which spoon has more? Here are magnetic domains on two samples of magnetic material. Which set of arrows is more aligned? Here's a map of precincts voting in favor of a proposition. Which set of dots is more concentrated? Well, I think you're beginning to get the picture. Here's a list of common statistical tools that we can use to make our analysis visual and intuitive to our audiences. Intuitive meaning it will be easy for them to see a difference between the two samples. If it's easy for them to see the difference and the sample size is large, then you will not need to show the results of complicated statistical tests to prove that the effect is not due to random variation. Oh, you still do the test. You just won't need to show them to your audience. I'm going to go through each method, and you should be able to interpret the data instantly and reach a conclusion based on seeing it. You are responsible for the quality of an assembly. The final inspection yield was 90% last quarter, but your boss wants you to improve that to 95%. Your outgoing inspection team provides you with this analysis of the last quarter's rejects. Here's a table of data on defects on the assembly. Just a bunch of numbers. Let's make it visual. Here's the same data in a bar graph form. It's called a Pareto diagram. You have to reduce defects to improve yield. So where do you want to focus your resources? Could your final assembly have defects in more than one category? Sure it could. Whether the sample accounts for that depends on how the inspection was done. Was it fail on the first defect? Or did they go on and inspect the complete assembly and record all the defects they found? This is a Pareto diagram of defects found on gas distribution panels used in semiconductor fabrication tools. To make this Pareto diagram, we sorted the defect category data by size, which is bigger. The vertical axis is the defect count. The horizontal axis is the defect category. Arranging the counts from largest on the left to smallest on the right makes it instantly recognizable which problems are the biggest. In 100 samples, there were 30 defects. If I need to cut the defects in half, where should I focus my efforts? How do you think I got this data? We could have put a simple tick sheet out on the manufacturing floor and asked the test operator to make a tick mark by each defect as he came across it. Do you think this kind of plot is intuitive to someone without a knowledge of statistics? Of course it is. Now let's take a look at our old friend, the run chart. You're concerned about tool wear on a machine. Normally you change the tool after 200 parts. You decide to make a run chart for the dimension of a feature versus the parts that you have run on that tool. You begin measuring parts and you get the following data. What do you conclude? Well, first of all, what's the characteristic we're concerned with? That critical dimension. Is it a variable or an attribute? Well, it's a variable. Is it discrete or continuous? It's continuous, but it does have limits. Here's the run chart of the critical dimension on that machine part. Every time a part is made, we measure the dimension and we plot it on the run chart. The dimension measurement is shown on the vertical axis and the sequence of the part is shown on the horizontal axis. Each time we make a tool change, we reset the sequence. 4 tools were used with the tool change about every 20 parts. We have an upper spec limit and a lower spec limit that we've drawn in so we can see where the dimension is relative to those 2 spec limits and what's happening to the dimension during the tool run. It starts out very close to the lower spec limit, but it gradually moves up towards the upper spec limit the more parts we make. Why do you think that happens? Probably due to some tool wear. It looks like there may be tool wear a little faster than we thought when we set the tool replacement point at 20 parts. When you look at the run chart, can you see when the tool should be replaced to assure that all parts meet specs with a high degree of confidence? Probably somewhere around 14 to 16 would be optimal. It's pretty intuitive. I don't really need to do a sophisticated statistical analysis. I can just eyeball the graph and draw my own conclusion. A run chart is a plot of some characteristic in sequence over time. We can add details to the run chart like spec limits or markers that denote significant events. In this chart, there were 2 process changes noted. So I have a total of 3 different populations. The first population is from the left-hand side of the chart all the way up to the first down-pointing orange arrow. Then I have the population that occurred between the 2 orange arrows, and the third population is all parts made after the second orange arrow. The arrow indicates a change in the process, so I'm going to ask you now which process gave us the best yield. In this case, yield means pounds of resin per run. up to the first arrow, between the first and the second arrows, or after the second arrow. Our goal was to get at least 100 pounds of resin out of every run. It looks like between the first and second arrows probably gave us the best yield. Okay, you're beginning to see how things work. Next, let's take a look at dot plots. A dot plot helps us understand the frequency of occurrence of something. For every observation, we put a dot into the corresponding bin. The bin corresponds to a key metric or measure or data point that we have defined for the product, and it describes a characteristic of the product. In this example, we're plotting a discrete variable which can only be a whole number. These 60 dots represent the entire population. Can you estimate the mean and the range? This was the sum of the up faces on two 6-sided dies which were repeatedly tossed. You can see that the mean is somewhere between 6 and 8, and we know that if we did this thousands and thousands of times, the means would be 7. The lowest part of our distribution is at the number 2, and the highest part is at number 12, so we can conclude it was two 6-sided dies that were being tossed. And the distribution looks kind of like a normal distribution. It has a peak in the middle and is pretty symmetric on either side. Dot plots help us compare the shape of a distribution and help us compare measures of the center of gravity and how widely spread or dispersed is the occurrence of these values. So shape, center of gravity, and dispersion, easily compared or analyzed using a dot plot. Dot plots can show us a central tendency, the mean, the average, and the median, as well as a dispersion around it. By stacking dot plots, you can easily compare the average and range of two populations. In this example, we're comparing the downtime for the day shift and the night shift. Every day we look at the amount of downtime that each shift experiences, and we plot a dot in the appropriate bin corresponding to that shift's downtime. Now you can see that the day shift tends to have a lot higher downtime than the night shift. You can also see that both the day shift and the night shift have some outliers, whereas the day shift, they are towards the low end of downtime, and the night shift has some outliers towards the high end of downtime. When I see a comparison like this, it makes me want to get the two shifts together and have a conversation about what is causing the downtime and how do they respond to it. Now, a dot plot doesn't always have to be dots. Sometimes it's easier to make a bar chart out of it. There are three ways to determine the center of your data. The mean, by adding up all the values, dividing by the number of samples. It's good when the dot plot is symmetric and there are a large number of samples. The median is an equal number of points on either side of the median. It's good when the dot plot has some extreme outliers. The mode is good when the data shows a long tail on one side. It's easy to see, but there may be more than one mode. The mode is the most frequently occurring number. Here's another dot or frequency plot shown as a bar graph comparing two different samples from the same population. Look at the dispersions. The lower sample is the same sample as the upper sample, except I threw out any results that were 2 or less or more than 5. The lower plot is what I'd expect to see from a supplier who was producing a part and then grading the parts into categories and sending me the center of the population. For this next example, I'm going to send everybody out to the warehouse, and we're going to collect some data on the time it takes to complete a shipping document. You collect data from 2 material handlers across 100 samples each. And you decide to use the dot plot as your method to analyze the data, but you don't want to do it by hand. So you load the data into an Excel spreadsheet and use the data analysis tools to create a histogram. Here's your histogram. What do you notice? There's a pretty wide spread. There's more than one peak or mode. Let's do some more analysis. Let's do a separate histogram for each material handler. Now what do you notice? Material handler 2 takes longer than material handler 1 to complete an order. The dispersion or spread is about the same, and the graphical display makes it easy to see and make comparisons. Now let's look at the box and whisker plot. It's a good way to graphically compare a lot of populations on one page. The box and whisker plot is a kind of frequency distribution plot in a very small space. It makes it easy to compare the center of the data and the dispersion of the data. Why do you think the rightmost plot is only a single line? It could have been there was only one sample, or maybe there was more than one sample, but all samples had the same value. It's a good idea to show the number of samples for each box in your box plot comparison. The single cross above the Germany category is an outlier data point that was not considered in plotting the maximum. Be sure to explain why you did not include outliers. Minitab or Excel 2016 will construct these box plots and whisker plots for you. Earlier versions of Excel have something called a stock plot, which is very close, or you can manually create a box and whisker plot. Do a web search for creating box and whisker plots in Excel to learn how. The next visual plot we're going to look at is called the cum probability curve, or sometimes it's called the percentile curve. It's really good for numerical data. We plot our probability percentile of x on the vertical axis versus x on the horizontal axis. Each point on the graph then shows the probability of occurrence of a value less than x. We could also use it to plot failure rate by letting the vertical axis equal the total percent failed, and the horizontal axis equal time or cycles to failure. You can make these charts on Excel using the data analysis pack rank and percentile function. Here's how you make your percentile chart. First, you're going to create a spreadsheet, or just even a pencil and paper. You take 2 columns. In the first column, you rank order the data from lowest data point to highest data point. And then for n samples, you divide 100% by n. In the second column, you're going to enter in the percentile. So for the first data or lowest data value, you're going to start with the percentile equals 1 minus 0.5, all quantity times 100, divided by n, so that you're going to offset that first data point down a half step from 1 over n, or 100 over n. Then you're going to enter the percentile in column 2, and then for the second lowest, you're just going to increase the percentile by 100 over n, and so forth. Then you make your plot of the percentile on the vertical axis versus the data value using the scatter chart function in Excel, or again, you can do this with pencil and paper. Now here's how you might use that. Let's say you're making a product that must contain 5 milligrams of ingredient A per unit. You're required to take a sample of each production lot and either accept or reject the lot based on the average amount of ingredient A in that sample. There are two proposed methods to manufacture the product, and you want to know which is going to be a higher yield of good lots. So you make 20 lot production run by each method, and you pull a 5-piece sample from each lot and measure the average amount of ingredient A. You gather up your data, put it in a spreadsheet, and you show it to your boss like this. Method 1. The average amount of ingredient A got very close to the desired amount, and it costs less to run. While in Method 2, you just exceeded the required amount of ingredient A, but it was more expensive to run. The boss looks at your data and says, "Good job, we'll use Method 1. Realizing that Method 1 might produce more failing lots, you ask for a little more time to do a more thorough cost analysis. You rush back to your desk and you create this percentile or cumulative probability plot of the results, and you draw in the line showing the minimum amount of ingredient each product must have. With Method 1, you'll scrap about 60% of the product, while almost no product is scrapped with Method 2. You go back to the boss and explain that you must run 2.5 lots by Method 1 to get as many units of product as 1 lot by Method 2. So the total cost is equivalent between the two methods, but not as much capacity is required for Method 2, so you can make more units per day. The boss says, "Look, just dump more ingredient A into the process, raise the average, and everything will pass, and the cost will be lower." You point to the two lines and say, "We could do that, but we'll be wasting ingredient A, and our product will not be consistent. Look at the slope of the two lines. Ideal would be a vertical line at just above 5 milligrams. Method 1 has a much higher dispersion of ingredient A than Method 2. If I put more ingredient A into Method 1, my costs go up and I may exceed the maximum amount allowed. On the other hand, I can put a little less ingredient A into Method 2 and still pass all of my lots. Since Method 2 is tightly controlled, we'll get a more consistent product. Not too much and not too little either." "Okay," says the boss. "These charts really make the difference between the two processes stand out. Let's use Method 2. Now go cut the cost. You're killing me." Now let's take a look at scatter diagrams. Scatter diagrams are used to show the correlation between one variable and another. We usually plot the characteristic of interest on the vertical axis and a process input on the horizontal axis, or y is a function of x. This is a plot of load capacity of a single tire versus its inflation pressure. It looks like a straight line because the load capacity is a linear function of the inflation pressure. So there's a strong positive correlation between load capacity in pounds and inflation pressure in pounds per square inch. For linear relationships between x and y, we say there is positive correlation if y goes up when x goes up, and negative if y goes down when x goes up. No correlation if y behaves randomly as x changes. But correlation doesn't always have to be in a straight line. In this scatter chart, y is correlated to x, but the points are not in a straight line. The solid line is a trend line that's a polynomial fit to the points. Where would you set x if you had to minimize the amount of y? Probably somewhere between 3.5 and 4. Next, let's take a look at concentration charts or skeleton charts. They show where something is happening. You draw an outline or picture of the item, and each time an event occurs, you mark the location of the event. This concentration diagram shows the location of injuries as reported by welders in a shop. I started keeping skeleton charts for my high school basketball coach. Every time someone took a shot, I wrote their number on the map of the basketball court. If they made their shot, I drew a circle around it. Then it was easy for Coach to see who was hot and who was not. Look at this chart. Where did we take the most shots as a team? Right around the foul lane. Who's the best outside shooter we have? That's right, number 5. Who's the worst shot? Number 1, he didn't have a single circle around his number. This manufacturer was trying to reduce the number of gas panels that had to be reworked due to leaks. The engineer asked the operators to record where on the panel the leaks occurred. He then asked the operators what was unique about the locations with the highest concentrations of leaks. Locations marked A were next to the edge of the enclosure, and the operator said it was hard to get the wrenches onto the fittings to tighten them up, while location B had a manifold design that was very hard to align. Using this information, the engineer was able to alter his design and reduce the number of leaks. Okay, time for a little review. A population is all products or services produced by the same method or process. A sample is a selection of products that is less than the full population. A random sample is a sample selected from a population such that each member of the population has an equal chance of being selected. A characteristic is something that describes the product. An attribute is something that the product has or does not have. A discrete variable can only be a whole number, while a continuous variable can be any real number. Data is a number that could be a measurement, a count, or a ratio. Statistics are numbers that describe a sample. A Pareto chart is a bar chart that's used to sort categories by significance. A run chart is a result that's plotted versus time or sequence, and it's used to spot trends. A dot plot is a frequency histogram or probability plot used to compare center and dispersion of data. A box plot is another way to compare the centers and dispersions of several samples from several populations. A cumulative probability plot or percentile plot shows the percentile of X being less than some number. It's used to predict yield or failures. A scatter diagram plots a result, Y, versus an input, X, used to determine interaction between a variable factor and the result. And a concentration diagram determines the relationship between location and effect. Summing up, I want you to keep things as simple as you can and show your results graphically. Decide what's important, get the right data, use the right statistical analysis tool, and then graphically display the results so it's easy for the audience to reach the same conclusion that you did. Well, everyone, thanks for tuning in to another Johnstone Global video. If you have any questions, email me at jjohnstone4007@gmail.com.